Well, students, in my previous lecture I discussed about the PTO driven tractor rotavator. Now, we will talk about design of a tractor PTO operated rotavator. We will see what are the various design nuances which are important in designing a PTO driven unit. In the market, we will find that there are various manufacturers and they are manufacturing different sizes, different horsepower requirement ranges and different types of blades, as well as the other important features of those. So, it is very essential as a designer, you must have an idea as to how we should go about the design of such a rotavator. Well, when we know about this design, it is very important to know how the power comes to this rotavator, or how power is taken from the tractor for this rotavator. Now, let us have a look at it. See here, the tractor engine is there. Now, from the tractor engine we know that the power of the tractor engine is available at the end of the crankshaft. Now, after the crankshaft we have the clutch and flywheel. So, flywheel, clutch, and after that then we will have the transmission. So, once it goes into the transmission, then we have certain losses. At the end of the crankshaft we get certain power of the tractor depending upon what is the power which the tractor has. We will get some losses, we have just estimated about 5 to 10% losses sometimes. Now, after this it enters into the transmission. Now, there could be various types of transmission depending on the tractor which is being used, or if you are asked to have a certain type of tractor transmission which is already given to you. For example, if you are given that a 6+2 gearbox, or a 8+2 gearbox, or a 10+2 gearbox. So, depending upon that you will find then that what is the type of output that I am going to get. Then it comes from the transmission, it comes to the differential here, and it is well known the differential's tasks about what it does and where its importance now, and how the power from this goes to the rear wheel, the two rear wheels. Now, from we know that in the transmission this to the PTO, power to the PTO goes from the lay shaft or the counter shaft. This is directly connected to the PTO here. Now, in some of the tractors you will find ground PTO and engine PTO. Not many tractors have this thing, but in some of the tractors you will find like this. So, this is how the PTO is available to you. We also know that this PTO is not only a simple PTO, there are different variations of this PTO, maybe 6 splines, 21 splines, I have explained in my earlier lectures as well. And then we have shown also that what is the RPM. The RPM of the 6 splines is about 540 RPM plus minus 10, and then 21 splines where we have 1000 plus minus 20 RPM, depending on that. Now, once this PTO is to be used and moreover, we have the maximum power of the tractor available at this PTO. Now, at this PTO then how to take the power out, because we have to utilize this power which is rotating in one plane and we want it to be changed to about 90 degrees or so. So, then we have to have some sort of a arrangement for attaching this PTO to the gearbox of the rotavator. So, a rotavator is over here and then it will have a single gearbox. Now, what is there in this gearbox? Yes. Now, you just have a look at it. See the gearbox here, this is the gearbox here. In this gearbox we have the arrangements. You can see a shaft over here, it's a bevel gear here, another shaft which has bevel gear here. So, this is the arrangement by which we are in a position to change the rotation of this to this about 90 degrees. And the universal shaft. Now, you might have seen in other course of your study that how we can connect this PTO to other shafts or other units. Sometimes this is a longer unit which is known as a cardan shaft, and this shaft has at its two ends there are two universal couplings actually. These couplings are known as universal Hooks joint. You can also have a look at this at the tractor here, you can also have a look at this. There are various types of this, we may see this in the later slides, that how do they look like, this universal Hooks joint. So, this joint has unique advantage and unique formation such that even if there are certain variations in the inclination of this, it will take care of that. So, using this cordon shaft and the two universal hook joints on the two ends, this PTO is connected to the gearbox, to this gearbox here, and then comes to the rotavator. Now, in the rotavator, as we have shown earlier, that this after this, now the power is available here. Now, since the power is available here, how do you get this power to rotate the shaft, because this has to be rotated. Now, see, we just told you that earlier, in fact, using a chain sprocket, you can get the shaft of the rotavator operated, or you can have a gear arrangement. Now, here a gear arrangement has been shown, which we call side drive, which is for the gears. Now, this, and at the end of this, we will have the shaft of the rotor connected. So, the shaft of the rotor is connected over here, so that the power goes to this. That means, if we see from the beginning that we have the tractor here, the power is available at the end of the crankshaft through clutch, and then it enters to the transmission. From the transmission, it goes to the differential, and then goes to PTO. Of course, the PTO goes directly from the counter shaft, it comes to the PTO here, and with the PTO then we have the cordon shaft using the two universal hooks joints, we have connected to the gearbox, and then gearbox with the side gear we are connected to the shaft. So, this is the way the power flow takes in from the tractor to this. So, you may have certain losses which are taking place. We will have a look at these losses, or actually how much is the power available, because it is very important for you to know how much is the power available. Then only you can see, design what should be the size of the rotavator, how many blades will be there, what will be the width of that, what will be the diameter of the shaft, and so on and so forth. So, it is very important to know about these aspects initially, right. So, we would have, now we have seen that this after the rotor will have blades, and these blades will operate. Now, in rotary, let us have a look at it. See, the rotary machine cutting resistance is determined by the peripheral force K 0, which depends on many working parameters of the machine. Now, A here is the specific work. Now, what we want is, we must know how much is the total quantity of work, that is how much amount of soil volume it will handle, because that will be the basis for actually design, because that is the load which the implement or which the power source is going to handle. So, we must have an idea about what is the amount of work that it will handle. So, this specific work A is given as m times twice pi z, which is already known to you, the number of working elements, L, which is also known to you, length of the soil slice, which we have discussed in the previous classes. Then A and B, A is the working depth and B is the working width. Mind you, we are slightly very cautious, or one must be very cautious about the units which have been used here, because then if you change the units, or if you do not use these units, then the parameters which are there will have a different value. So, you must have a look at this and be cautious about while using this particular equations. So, this is the equation which gives you the value of specific work in this fashion. Now, sometimes this Kx, the workforce, this Kx, sometimes this Kx is very small, resistance or pushing force of the machine, actually resistance or pushing force of the machine, the component of the cutting resistance parallel to the direction of travel. Now, this resistance may not be to that extent sometimes, and that is why it has been given a very small, you can see that this particular factor, and many a times if we ignore this part, then the specific work A simply comes to this value. Now, So, and this value then has two important components, one is the static work and the other is dynamic work. So, these two are then added up to A is equal to A is equal to A 0 plus A B. So, what we want to tell through this particular slide is that the amount of work which the rotavator will handle is very important, and it will help us in taking the total amount of power to be generated or power to be designed for the power source for a particular type of design of the rotavator. Now, let us go to the next part of it. Yes. Now, how we had talked of the two parts of the specific work, we talked of A 0 and A B. One was a static specific work, the other was a dynamic work. Now, what are these and how do we get these things actually? Now, these have been worked out over a series of experiments by various researchers and then compiled, and then we are all over the world we are using this sort of information. So, I have also picked up here for your knowledge and then kept it here. You can see the static specific work, sorry. Yes. So, static specific work here A 0 is dependent on important C 0 K 0. Now, what are these C 0 and K 0? Now, this C 0 and K 0 you have to get from the table which has been prepared here. This talks of the type of the machine, which is the rotavator, the rotary hoe or another type of plow. Now, these are standards and made worldwide. So, you need not bother about this, but then you must have an idea, because this has been created for a worldwide audience for use. So, rotavator rotary cultivators, for all the rotary cultivators you can see that the type of knives, the type of say L type of knife or a bent one. So, you can see the working depth, if the working depth of operation of this is between 10 to 15 or 3.5 is to 6 or 6 to 12 or 5 to 15, then the length of the soil slices. We can find out the soil slices. We have already obtained the soil slices in our previous lectures. So, we know how to get those soil slices using the various parameters, the length of the soil slices, which will have a dependence on the total draft requirement or total value of the volume of the soil, which is actually being handled by the power source. So, it is very important. So, if you have those values also known to you here, then and in the soil, in a particular soil, because the soil will also vary from one location to another location, the type of the soil, there are various details which are required for the soil. In fact, it is not within the scope of this particular lecture to talk about the different type of soils, but then as an engineer's point of view, if you just talk about the tilled soil on meadow soil, tilled and meadow soil, and this, if you only take these two aspects and then go ahead, then we will find that the values of C 0 and K alpha u is the dynamic resistance, is a coefficient of dynamic resistance, U b for the forward speed and U I for the rotation of the peripheral velocity of the rotor. So, for these two we can get the value of C 0 and C from this particular table. So, once you know this information with regard to the soil, the length of the slices cut, the working depth and the type of blade used in the rotavator, you will be in a position to get what is the static specific work here using this equation, and then dynamic specific work also you can get from this equation. Now, this equation talks of alpha v and this alpha talks of alpha u. So, alpha v with v square, which is the velocity of the forward velocity of the tractor, and u is the peripheral velocity of the rotor. So, using that information we can get the value of b, because it talks of the specific dynamic specific work, provided the length of the soil is constant. Now, here this is one thing which needs to be looked into, length of the soil is constant. Actually, although it is a assumption, but many a times this may not happen. This may not happen many a times. The soil length may vary depending upon the speed and depending upon the design. It may vary, but we assume here, we are assuming that the length of soil sets is always constant. So, then the working set on the peripheral speed or on the speed of the machine travel. We can get this dynamic values of A B, that is the dynamic specific work. So, once we get the A 0 the static one and A B the dynamic one. So, we will be in a position to get the two details, and there is also a relationship between this alpha V and alpha U. Now, this relationship also has been found out, which exists between the coefficients of the dynamic resistance between the forward speed and this. This has a relationship, because until unless we have also seen that U and V has a very close relationship so far as the power required is concerned, so far as the slices cut or total performance of the shaft is concerned, rotavator is concerned. So, that is why another relationship has been found out, and it is given as alpha V is given as alpha U times U by V whole square. Kindly check that the unit should be taken care of properly whenever you do any problem, etc. Well, so if we have to design the rotavator for say for a 30 horsepower tractor. So, for 30 horsepower tractor, then what are the considerations? We have already discussed all the details of how from the engine the power will come. Here also in brief it is still given. From engine to transmission, we expect that there will be some losses of power, let us say about 10% loss of power. From transmission it comes to PTO, where we are expecting other 10%. So, maybe about 80, 85 or 90% power is available at the PTO. From this power we need to take the maximum power to this rotor, and that is why it is very important that you should design in such a way that the rotavator is matching the power. Of course, there should be a certain buffer of the power source, because of taking care of some of the eventualities or some of the obstacles which may come in the operation. So, for that we must have a slightly safety factor as well, but then it must match as much possible to the power source, the requirement. So, that we can say that it is a good matching implement to the power source, and that is what is the crux of this particular design as well. So, let us see the there is a mistake here, it should be actually brake power, brake horsepower is say 30 horsepower. So, the power available at the PTO. Now, power available at the PTO is varying from about 80, 87, we have taken 87, it can vary from somewhere from 86 to about 90% of the so. So, about 85 to 90% power is available at the PTO, which we have I have also earlier told you that this is the location or the power outlet where we get maximum power from the tractor. So, we have taken about 0.87. So, 87% of that. So, we get about 26.1 horsepower. Now, this horsepower, so 20% loss through the transmission. We assume that let there be 20% loss, just slightly higher we have taken, and in fact, these will go for thinking of the factor of safety that we are keeping so far as the unseen, unforeseen situations when the implement is operating in the field may come through. So, for that let us say about 20% loss. So, therefore, the power available at the shaft is about this 80% of this. So, about 15.6 kilowatt is the power which is available at the shaft of the rotor. Now, if this is the power to be utilized by the rotor, what should be the other details? For example, let us consider the forward speed of the tractor. Now, the forward speed of the tractor has a greater bearing on the rotation speed of the rotor of the rotavator, because we have talked of U by V ratios. So, U by V varying from 2.5 to 5 or so, we need to look into this. So, we can think of a value where about 2.5 to 5, and hence U by V has to be considered over here. Now, one consideration is the speed of the tractor. We know that the tractor, particularly for first plowing or even for second plowing, we do not go speeds which are very high speeds, because the condition of the soil is not well known, and hence we go about 3 to 3.5 kilometers an hour or so, varying from as low as 2.5 kilometer to as high as about 4 kilometer in some of the high horsepower tractors. So, we will take about say 3 kilometers per hour here. Now, 3 kilometer per hour here the forward speed, that is V. So, if we consider a U by V ratio anywhere between 2.5 to 5 and let us say it is 5, then we are getting the rotor speed to be 4.17 meter per second here. Then we know what we know here that twice pi, in fact, this should be pi here. So, if I write this thing here as twice pi n r by 60, where r is the radius of the shaft. We can see here that this is the so, if you take this so this is the radius over here. So, we can say that the rotor speed well, this should also be in the lower case, but does not matter. So, this is now from here we can get what is the RPM of the rotor. So, we get the RPM of the rotor about 260 revolutions per minute. Now, power K 0 into twice pi n r by 60 is K 0 is this value, because K 0 into twice pi n r by 60 is this. So, we can get what is the value of K 0, which is the peripheral force constant and at a constant arm length of r at this point, what will be the value here K 0, because this is the one where we need to know as to what will be the forces which will be entering into will be encountered by the blade over there. There will be torsional forces, there will be bending forces. So, those will have to be found out in order to actually design and say that the design is safe and the rotor is designed, rotavator is designed. Now, go to the next slide. Yes. So, if we take up the specific work A is equal to A 0 plus A B, sorry. Specific work. So, we need to know about what are the details of this. One, which I have explained earlier also, that you must know what is the total specific work, because that becomes the basis for your design. How much is the volume of soil the rotavator will be handling, the blades will be handling, and then only we can think of the power source. So, it is very important to know about this part. So, A to A 0, this is over here, where A 0 is this, A 0 is as per the details, these values are already given here, where C 0 is 2.5 to 5, K I is this. These are the constants, or these are the values which we take from the table or the available or literature, and from there we need to use these values. So, A 0 and A B. Now, these values, A B comes to be this here and A 0 comes to be this. So, total A, which is the total specific work, comes out to be 1.144 kg per centimeter square. Now, this is the value which has been theoretically found out. Now, one may be cautious, because this is the value which has been found out. At some point or the other, we have to have some factor of safety, and that factor of safety has to be taken into consideration either at this stage or at some other location. Let us see where we should come for this. So, moment acting M. So, what is the moment? Now, we can know here that moment is this is the details of the moment, because it will talk of the specific work, then this will talk of the number of blades, etc., which were the Z was the number of blade on one plane, then L is the bite length, A is the depth of operation, and B M is the total width of the machine. So, if we talk of the total moment here, the moment acting upon M is this. Now, we know that so we know that L is V by U is equal to this, then M is K 0 into R. So, putting values and solving above equation, we get width of the rotor here, sorry, width of rotor, total width of the machine as this here. So, this is the total width of the machine. Now, once we get the width of the machine, we are we know now this should be the maximum width of the machine for a 30 horsepower tractor. Now, depends on whether we actually take 1.63 or we should take slightly lesser, or we can still take maybe 1.7 meter or so. This is a consideration which the designer has to look into depending upon his power source. Okay, let us go ahead. So, the number of discs, then once we know, we would like to find out the number of discs, and width of the machine is known to us here. Then the in between, if we have to assume certain things, we would like to assume what is the spacing, how much spacing you would like to give between the discs on which the blades are fitted onto the rotor. Now, we would like that this has also a consideration with regard to the total length of this particular blade. For example, if this is the blade here, it has something to do with this also, this length, because then only you should see that the next one comes somewhere there. So, therefore, we on these considerations, let us say it is about 20 centimeters. So, if this is 20 centimeters, so the number of discs on the shaft will be about, number will be 8.16, we can take comfortably 8. Now, number of blades. Now, how do you fix the number of blades? Generally, what has happened is that on the discs which are there, if you find the one designs which are there, many a times on the two ends we keep only 2 blades, and in between there are 4 blades are kept into the other ones. So, keeping that into view, we can have a look at this, that out of the 8 discs, the 2 discs will have 2 each and the 6 discs will have 4 each. So, that way 2 into 2 4 and 6 into 4 24. So, that is 28. So, total number of blades will be 28. So, now each disc consists of 4 blades, but other as it has been said over here, right. The arrangement of the blades on the disc at an angular angle, this is very important. At what angular position you are going to put, this will be about 12.85, it has been found out, because we know that how many are there and how many are there in a plane, and then for 360 degrees what will be there. Now, this orientation is very important. At what this will talk of actually the angle at which, if you talk, this is the from the center. So, we are talking of this angle. So, what is this angle? This angle is about 12.85, because then it will talk of this value which is called r theta. So, this distance, this theta is this distance where r is known to us, which is the shaft radius, radius of the shaft, and theta is this angle. So, we will know as to which location these blades are fitted. Now, then the blade design is very important. Blade design, you can see here that the front view and the side view of the blade designs are given. We know that on these blades definitely there will be bending stresses and torsional stresses which will come on that, because when they handle so much of soil with their depth and their width of cut. So, we will consider these two aspects, the bending stresses and so forces acting on one blade, K0 is this, where we can consider the details of, these are the general details of thickness of the blade, width of the blade, etc., as it has been shown here. We will go ahead. Yes. So, we can get the bending, we have got already the bending stress. Now, we will get the torsional stress here, and from standard design shaft design formulae, we know that the equivalent stress is given as this. So, once we know the equivalent stress, we should be in a position to find out what is the width of the blade, as we do in case of all the shaft design, etc. So, here in case of this case, say for a high carbon steel, we have taken a value of 1080 kg per centimeter square for the equivalent stress, and then once you use this value in this where the other values of this and these are known, then you can get the value of width of the blade as 5.82 centimeter. One can take the blade to be 5.82, maybe about 6 centimeter blade one can take, and then the thickness of the blade can be found out from a ratio of BE and HE. So, you can take this, and B comes to be 0.971 centimeter, maybe about 1 centimeter or so can be taken comfortably. So, if you conclude then that what we have designed and what we need for a 30 horsepower tractor, these are the details of the design of a rotavator, PTO driven rotavator. Now, this design can be utilized for other horsepower, and depending upon what type of rotavator you want, what design of the blade you want, what type of soil you have, all these considerations you need to look into for the design of the rotavator. Well, you can have a look at this. The total power is the total power is about 15.6 kilowatt. The specific work done is about this. Then the total width of the machine is 1.63 meter. Number of discs 8 here, and the total width of the dimensions of the blades are right here. These are the dimensions of the blades. So, I think through this we have explained as to how you can design a rotavator. Now, it is up to you to think of the change in the material depending on the type of the soil that you have used, and the horsepower of the tractor that you have, and the conditions in which it is to be used, etc., etc., and for the purpose for which it has to be used. If it is only used for mulching operation, then you can think of something else. If you think of only tilling operation and preparing the field, you can think of a different design, and so on and so forth. I hope that you have been in a position to understand what I wanted to mean by design of a rotavator. We look forward to your questions and queries in the later course of time. Thank you.